So while you're figuring that out, this compound, now this is called a combustion reaction, where you're going to go ahead and figure out a formula based upon the analysis of the product and how much you started out with. And it's just a normal combustion reaction, burning. In every combustion reaction, you get CO2 gas and H2O. You always get those two for sure. And if somehow, some way, you can measure how much CO2 you get and how much H2O you get in weight, then that lets you figure out how many grams and eventually moles of carbon you have, and how many. And then we're going to use water the same way. All right, so you get 3.60 grams of CO2, 9.21 grams of H2O, and then you start out with 3.59 grams of CH&O. So you would go, what, 44 to 1, right? And then you would go, for every 1 CO2, you have what? 1 carbon. Is that right? Is that how you guys did it? So how many moles did we get? 3 digits.
0.0818.
0.0818 moles of carbon. So look at this. That's how many moles you have here. So you kind of see what we're getting up to now. We're gonna get mole ratios here, and then we're gonna take the smallest one. So now do the same thing with the H2O, because you know all the H's come from where? Here. So all these H's that are in H2O come from your reactant. So then you'll do the same thing, and you'll do it with water. You will take the 9.21 grams of H2O, and you figure out moles of hydrogen. Okay, so then you have another amount of moles that you're going to work with, right? Now, you may want to, I stopped at moles, but you may have to find grams of carbon and hydrogen. You will have to. So, you have the 0.018 moles of carbon. What I'm going to have to do is take it one step further, and I'm just going to go ahead and take that value and then multiply it to get my grams. I put 1 mole of carbon down here, and then 12.01 grams up here. And then I'll get my grams of carbon. And the reason I have to do that is because I'm going to have to eventually go back and figure out how many oxygens were in the original compound. So I'll find out moles, and then I take it one step further to find grams. Because you're going to have both in this process. You guys have any questions on what I'm doing here? Okay, so the first thing I did is I found my moles of carbon and hydrogen, and it's 0.0818 and then 1.02. Is that what you guys got?
Yes.
And then all I did was say, I'm going to need to know grams of both of them, because I need to go back to this value of grams here. Now, what makes up that weight? Carbon, hydrogen, and oxygen. I have 2 of the 3. I got carbon and hydrogen. I just need to subtract those 2 from 3.59, and what do I have? Oxygen. Right? Because the law of conservation of mass says my original compound is 3.59. It must add up to the carbons, hydrogens, and oxygens. Now these 2 oxygens on this side, I cannot use those directly because O2 is adding into that weight. So I'm going to take those 2 values, add them up, and then subtract.
Mr. Graham,
Yes?
in the equation for the moles of H2O to moles of hydrogen,
Yes.
how do you come up with the 2 moles of hydrogen?
It just says for every 1 mole of the molecule H2O, I'm going to have 2 moles of hydrogen atoms in there.
Yeah, but like the equation wasn't balanced, right?
Right.
Well, yeah.
It's right, but I'm just using the balanced, I'm just using my definite ratio here.
Okay, so
And so it doesn't matter if it's balanced or not, because I'm looking at it internally, the H2O internally, because I don't need to look at the balanced equation otherwise. Yeah, it can kind of get confusing. It's like, okay, when I look at the equation, you know, how do you get that? Because we're used to using the coefficients in front, and we're not doing that. We're just using the ratio of the moles of it within the equation. So then what we do, did you guys find oxygen?
Yeah.
So then, you guys can do this without me. I'm going to go ahead and write this out. What I want you to do is with your moles, then figure out your empirical formula with your moles. So you got the grams of oxygen, you convert it to, now, you guys didn't use 32, did you? For oxygen to find the moles? That's sometimes students do that because they think O2. So sometimes people will convert moles of oxygen and they'll use 32 instead of 16. You guys got to use 16, right? Okay. Just want to make that clear. It's not a pretty ratio. We're going to have to find something we can multiply the 12.5 by and the 1.2 by to get them the whole numbers. What would that be? So we multiply that by 5. Would that make that a whole number? No. Okay. We'd have to multiply it by 10, right? So this would be 12. And then we multiply this by 10, right? And then we multiply that by 10. So it would be what? C10 H. I'm just doing this order of the original equation, CHO. So CH 125. And then O would be what? 12, right? Is that correct? So this times 10 gives me 12. This times 10 gives me 10. This times 10 gives me 125. Now, that's not going to be possible because you can't have that many hydrogens. Okay? But so it's the numbers are mixed up. I just took it from a sheet that I'd made up and probably didn't make corrections to. But that would be the equation associated with the ratio. Does that make sense? Yes.
How far? Cause like 1.2, could that round to 1, or is that too far up?
That's too far up. So it'd have to be like, to round to it, it had to be like 1.01 or 1.02.
So it has to be that close.
Yep. Yep. Good question. Yeah, you can't now, if you were doing the lab, then you may have to adjust that and say, well, that 1.2 might be error, so I might make it 1. Okay? And the 12.5, I might adjust it, and I say, well, that might be 12. Okay? Because probably maybe you don't have numbers that big. But, I mean, this should have worked out a lot better, and it did. And I was just taking the sample we had from last year and that. So, probably be smaller numbers than that in the future. Okay. All right. I'm not going to give you anything like that. We'll do one of those. We'll have a setup. We'll do one of those on Monday. Okay.